episode of the Brainstorm, the show where you don't think you'll learn anything until you do. I'm your host, Jamie.
And I'm Sabrina. On today's episode, we'll be welcoming two of our favorite scientists, Dr. Vandertramp and Dr. Vandertramp. They're sisters, by the way.
We'll be learning about electronegativity and polarity.
And also molecular shapes. So, without further ado, why don't we welcome our two favorite scientists onto the stage.
Hello?
Hi. So, Dr. Vandertramp, why don't we kick off this show with your specialization?
So I specialize in electronegativity and 3D molecular shapes. So as you know, opposites attract and likes repel. Atoms are made of crunchy negative exterior and chewy positive center of electrons and protons. The positive protons attract the negative electrons. The more protons in the center, the more they attract the electrons. But the electrons don't stick to the center. They whiz around in these things called electron clouds with all these funny shapes. The clouds have different levels too, and the farther out the electrons are, the weaker the protons hold.
So, if an atom has more protons, it'll have a stronger hold on electrons, right?
That's electronegativity.
Wait, but if it's already got a strong hold on the electrons, how will it share with another atom to make a bond?
If another electron comes along with stronger pull on electrons, it will steal from the first one.
Oh, so one of them will have all the negative electrons, and the other will have none.
Well, sometimes.
Okay. Jamie, why don't you take Dr. Vandertramp over to the lab to help her with her electronegativity experiment?
Sure. Okay, so here we have set up a little demonstration to show different bonding types and electronegativity. We have some paper clips that represent
The electrons.
the electrons. These magnets are the
Non-metals.
nonmetals, and then this magnet is a
Metal.
Okay, and we're going to see how the metal and non-metal attract the paper clips, which are the electrons, differently.
Alright, so first we have a metal, and it comes along and it has a few electrons. And then a non-metal comes along and simply steals them away. Because its electronegativity, so pull, is much stronger than that of the metal, so it takes them all. And this is ionic bonding because the non-metal has all the electrons while the metal has none.
And what is an example of that on periodic table?
So the metal would be something like sodium, and the
Okay.
non-metal is chlorine.
Okay.
So together is sodium chloride or table salt.
Okay, so that's just ionic bonding, it's that simple.
Mm-hmm.
And now covalent bonding.
For covalent bonds, we have two different nonmetals, one with a much stronger pull than the other one. So the weaker one has electrons, and then the other one comes along and it tries to take the electrons, but is not quite strong enough to take them all away. So they end up sharing the electrons instead of stealing. This is covalent bond.
Such as...
Carbon and oxygen, so carbon monoxide would not look like this, but you get the idea.
Okay, so that's just covalent bonding is sharing, whereas ionic is stealing.
Yes.
Okay, well, it's that simple for different types of bonding with electronegativity. And we'll see you after the commercial.
I have all the electrons.
Welcome to the Benzene Yoga Studio.
Life, peace, resonance. The Benzene Yoga Studio is a place where you can come to find rest and share your worries equally amongst the group. Release your stress and find serenity by stretching both left and right, up and down, and never being unbalanced. Our inspiration comes from the beauty of organic chemistry, how electrons, the negative part of atoms, become equally dispersed throughout the molecule, never lingering too long with any one carbon. Find your center, your release, and your resonance with us at the Benzene Yoga Studio. Call now to book your free first trial appointment with us here.
So, now that we know how they bond, what would these shapes look like in real life?
Well, Some of them are only on a single plane, like they're 2D. That's when you have two atoms bonded onto the single atom, like this. Or when you have three atoms bonded onto the central atom, like that. But then when you start to have four or more, they tend to stick out at odd angles, like 3D shapes. Like this.
Very cool.
And we draw them like this. See? Very simple.
I don't understand those drawings.
Yeah, why don't we have a little experiment set up, and we'll be right back after the break explaining how these shapes make sense in real life.
Hi, I'm Sig from Sig Sticks, where you get exactly what you pay for. And I sell shovels, real good shovels. And I'm smart too. I use my math and my science to do my business. If you want one of my shovels, you need to pay with whole numbers on the right side of the zero.
How many shovels can I get for $100?
3 shovels.
That's ridiculous and a ripoff.
Hey, $100, that's 3 digits. You get 3 of my shovels.
All right then.
Hi, Sig at Sig Sticks, where you get exactly what you paid for. Hey!
Welcome back, everyone. Dr. Vandertramp, why don't you tell us what we're holding?
So these are Vesper shapes. So this shape is linear. Linear meaning 2 atoms bonded to the central atom and on one plane. This is trigonal planar, meaning 3 atoms bonded to the central atom, also in one plane. This is tetrahedral. Tetra meaning 4, for 4 atoms bonded to the central atom. This is trigonal bipyramidal, with 5 atoms bonded to the central atom, and also bi means 2, and pyramidal means 2 pyramids. This is octahedral, octa for 8, also meaning the 8 sides on the Vesper shape.
No, but there are exceptions to these shapes. For example, we all know that water has 1 oxygen and 2 hydrogens, so you would think that it's linear, but the hydrogens don't claim all of oxygen's electrons. And because they're unbonded and they're both alike, they repel each other as far as they can. So, the molecule takes a new shape to accommodate the repulsion. This is called bent, but as we can see, it's tetrahedral because there are 4 things attached.
Very cool. So when we draw these molecules, do you have to draw the electrons every single time if they're not completely taken up by the other atoms?
You can draw the electrons, and that's called the electron shape, but if you don't draw the electrons, that's known as the molecular shape.
That's fascinating.
Now when you have something like this, where the overall shape is a little more symmetric, so let's say all the fluorines on the outside here are much more electronegative than the sulfur in the middle. Then for each of these, then say this side would be positive and this side would be negative. But because they're arranged everywhere, so it's all pulling out, then the opposite poles cancel each other out. So the overall thing is roughly positive.
Okay, so for this one would cancel out this one.
Da.
But in this case, they're not canceling each other out.
No, because it's bent.
Okay.
That makes a lot of sense. So now we have a little demonstration on polarity that they're going to show us with regular kitchen supplies that you can find in any of your cupboards.
You can do this at home too.
Make sure you have parent supervision.
And now the Vandertramp sisters are going to show us a little experiment on polarity and electronegativity.
So for this experiment, we will look at polar versus non-polar liquids in cylindrical container.
So basically we're just going to mix a bunch of stuff and see what rises to the top and what falls to the bottom. So for this experiment you're going to need liquid honey, cornstarch or baking syrup, dish soap, water with food coloring in it, and canola oil. So the first thing you're going to do is you're going to start by putting the honey in your first container on the bottom. There we go. So next we're going to add the cornstarch or baking syrup. Note how the 2 substances don't mix together. They kind of do. Well, they sort of do, but... And then dish soap.
little more.
One more. Okay, there's bubbles. Then water. Apparently.
These glasses suck.
Then canola oil. So now how each substance is slowly beginning to rise, the most non-polar molecules on the top and the most polar on the bottom. So after a little while, the substances will all separate and look like this. Ta-da!
Thank you very much, my dear sisters. As you can see, these substances do not mix because they're polar and non-polar. Well, we've had a great day learning about electronegativity and molecular shapes here on Brainstorm. Dr. Vandertramp and Dr. Vandertrip, thank you so much for coming.
Thank
Thank
you.
you. We'll see you next time on next week's episode of the Brainstorm.
They'll never mix. How many times do I have to tell you? Long live Mother Russia.
So why are you talking in that accent anyways?
My semester abroad. Yeah.